So it would probably be useful for you to go back and view the aldo condensation video just to get an idea or to remember what aldo condensations are about. And that can prepare you to be ready to understand more about Claisen condensations. This is just forming an enolate of an ester rather than an enolate of an aldehyde or a ketone. Claisen condensations can undergo the same type of mixed products that an aldo condensation can. And so if we see these two enols combined with each other with a strong base and heat, we're going to see 4 different products come out of this as well. And we're going to add some other reagents as well to show you kind of a reaction mechanism or a step-by-step mechanism of some things we can do with these Claisen condensations. So what we'll do first is walk through a self-condensation of this molecule. Afterward, I'll let you work on the other condensations and the products, and then I'll show you the products like we did with the aldo condensations. So here we go. Here's this ester, and what it will do with the strong base is the strong base will pull an alpha hydrogen off, and then that will push the oxygen up there, and we form this enolate. The enolate will then attack this position. But why does it attack that position? Because we dropped electrons down to here, and this bond had to break. The weakest bond always breaks when we move bonds around, and the weakest bond is this pi bond of the enolate. And so this will go out and attack this position. Now, it'll cause this bond to break then, the other weakest bond, the pi bond and the carbonyl. And so then what we see as products for this reaction are as follows. Now, oh, that's wrong. Here's an example of missing carbon. Don't do that. Okay, so here we go. Here's the bond, here's the carbon from the enolate bound now to the carbonyl carbon. And so this is what we form. The next step is that this lone pair of electrons will push back down, and now the weakest bond will break once again, and the weakest bond this time is between the carbon and the oxygen. So this pushes off that side of the ester. So the next product we form is this. This is a beta keto ester. Here's the ester, here's the alpha position, there's the beta position, there's a ketone. Beta keto ester. So, this is the final product of Claisen condensations. We're done with this first step. However, we have to do the rest. And realize that this is one of the products that we formed, because that's what was pushed off here from the enol. From the second one, I guess. So now, the next step is that we are adding this bromine compound, ethyl bromine, to this. And we'll add base with it. Well, I guess we still have base. The tendency of the strong base is we're going to just keep pulling hydrogens off and pulling hydrogens off since we have a strong base solution. So actually, the next most likely position to pull a hydrogen off is this alpha position here between the two between the two carbonyls. So the base will subtract one of these protons, and the reason it does that is because it forms such a good resonance structure or resonance system. Because if we pull a hydrogen off, we have a lone pair there now. And the lone pair can push up to this position and make an enolate, and then push these electrons here. These electrons can push back down, breaking this bond. It can go over here and do the same thing, or it can just stay there. Either way, it makes this conjugated system, because with when we're missing a hydrogen there, that makes this an sp2 carbon. So now that we've done this, this carbanion here also has the tendency to act as a nucleophile. And so what it will do is it will attack this carbon here and push the bromine off, just like any SN2 you've ever seen. This is called alkylation, because we've added an alkyl group, this ethyl group, onto this other molecule. So if we keep moving around the board, there's the molecule we have. Now potentially, and probably more likely actually, this hydrogen will be pulled off too. We'll form the same system, and we'll do it again. And so we'll actually alkylate this thing twice. So there's the new product, and we've done the second step. Let me write. So we've done Claisen condensation, we've done alkylation. Now the next step is to add sodium hydroxide and water. Sodium hydroxide added to this molecule will do only one thing. The hydroxide ion will push into a carbonyl carbon. This is the most reactive carbonyl carbon because the ketone is not as reactive as this ester. The ester carbonyl carbon has this other oxygen group destabilizing it, and so it causes it to be more activated for attack. So this will attack in here. What it does is it causes this to be pushed up, and then as this hydroxide is bound to this, these electrons will push back down and then push off this ester side. And so what we have now is the ester converted into a carboxylic acid. And now we have two of these that came off. One came off wherever it was, right there, and the other one came off right there. So that's this step, and that's called saponification. And you can find in any book or any website or any, about organic chemistry about saponification. It's really interesting, actually. The process that to convert fats into soap. That's what saponification is, making soap. Now we've got a couple more steps. The next step is an acid step, because really all these things will be deprotonated. This will be deprotonated because we're still in this strongly basic environment. And so after we add H3O+, everything will be protonated, and we'll be back to kind of more of a neutral situation. The last step is a tricky step, and it's cool, because this is called decarboxylation. Decarboxylation is adding heat to this molecule. When we have a beta ketone next to a carboxylic acid, we can eliminate the carboxylic acid. And so what happens is this kind of interesting set of steps where this bond will go up here and break. This lone pair will go and grab that hydrogen. That bond between the oxygen and the hydrogen will go to this position, which means a bond has to break on this carbon, and it's this one. And it goes there to form an enolate. And so now, if we look at this molecule, what's going to happen is we're going to have CO2 come off. That's this part right here. And then the rest of the molecule will remain. And we get that enolate. Or enol, I'm sorry. And then the enol will, of course, kind of convert and eventually become that. And so we end up with this ketone product as the final product, along with these side products, 2 alcohols and a carboxyl and a carbon dioxide. But this ketone is the final product of all of these reactions: the Claisen condensation, the alkylation, saponification, acid step, and decarboxylation. And so that's kind of the routine, or the set of steps that we usually incorporate with these type of molecules. And you should be familiar with all those steps. And now, do that with the other 3 products that you get from this reaction. And then turn it off, do those things, then come back and I'll show you the answers to the other 3. So here are the final products. This is the first product we got, CO2, 2 of these alcohols. The next one is exactly the same. CO2, this time the 2 alcohols are different, but it's exactly the same. This one's exactly the same, this one's exactly the same. So, these 4 Claisen condensations are the same. I suppose if you varied this side group here and had a bunch more things going on over here, on the enolate side, you would have more variability in these products. But we do have a variability in the alcohols that we make from each of these. So it's important to just remember these steps, what happens, be able to do a few of these problems by yourself, and try some of the practice problems that you have in the book or that you get from class.